Hi students. In this lecture, I am going to discuss Biot-Savart's law. Let us see what is it. It is observed that when we are placing a compass near a current carrying wire, it shows a deflection that indicates there is a presence of magnetic field near the current carrying wire. So now we want to get its magnitude and direction of the field, and see that is given by Biot-Savart's law. So consider a current carrying wire. It can be any shape. This is a current carrying wire, so it can be any shape. So here Biot-Savart's law gives us strength of the magnetic field and its direction due to current carrying wire. So here we are taking a one small element. Let us take its length is now dl. So now magnetic field because of this element at a distance r from that element, distance is r from that element. So at this point, strength of the magnetic field due to this element is given by dB bar is equal to mu naught upon 4 pi into I into dl bar cross r bar upon r cube. So r bar is the position vector of the point at which we want to calculate strength of the magnetic field with respect to the current element. I am repeating, r bar is the position vector of the point where we want to calculate magnetic field with respect to the current element. So this is now r bar. Okay, this is r bar. Modulus of r bar is now distance of that point from this element. Okay, and that is given by mu naught upon 4 pi I into dl bar cross r bar upon r cube. So from this we can say direction of dB bar is given by dl bar cross r bar. So we are knowing how to get direction of a cross product. Okay. And we have learned that in case of cross product, its direction will be normal to the plane containing both the vectors. Okay. So you can see here, if you imagine a plane that contains this dl bar and r bar, imagine a plane. Now in this case, this both plane contains dl bar and r bar. Then dl bar cross r bar gives direction that is now normal to this board plane. So in this case, we can see this is now into the board. Okay, that means at this location, because of this element, direction of field is into the board. Okay, so this is known as Biot-Savart, right? Now in this we can see mu naught. So mu naught is known as permeability. It is known as a permeability of free space, permeability of free space or air or vacuum. Okay, all are same. So mu naught is known as a permeability of free space or air or vacuum. And its value, mu naught, its value is 4 pi 10 power minus 7. Now you can see units here, units for mu naught. So we are knowing for magnetic field, units are Tesla, right? This is now Tesla. Tesla. Next, 4 pi is a constant. And you can see dl bar. This is a length. R bar. This also length. Length and length. This is now r square r cube, right? That means length and length. Length square. So remaining is now only length here. So Tesla into meter upon ampere. So it is now Tesla meter upon ampere. So like this, we can get units directly from this one. Okay. And here, 1 Tesla meter upon ampere. This is also known as 1 Henry per meter. So Henry is name of a scientist. Okay. So 1 Tesla meter per ampere. It is also equal to 1 Henry per meter. Right. And here we have one relation for mu naught and epsilon naught. So we are knowing epsilon naught is known as permittivity of free space or vacuum or it is air. Okay. So speed of light c equal to 1 upon root of mu naught epsilon naught. So relation between speed of light and mu naught. Okay. This is a relation connecting c, mu naught and epsilon naught. Okay. Now see how to use this one to get magnetic field. And you have to focus here direction of dl bar. That is direction of current. So here you can see this is now direction of dl bar. Okay, direction of current. Let us see now how to apply this. See the first one. So first we are going to calculate field due to a finite straight wire. Okay, let us see how to get it. So we are taking now a straight wire. It has a finite length. So take a straight wire. We want to calculate at some distance r from the wire. At some distance r from the wire. And if you join the ends of that wire to that point, if you join the ends of that wire to that point, that makes angles alpha, and this is beta. Okay. So we want to get now strength of the magnetic field. I assume current direction is not like this. This is current. So because of this current carrying wire at a distance r, we want to calculate strength of the field and direction of current. Okay. So now take here Biot-Savart's law. So because of one small element, strength of the field is given by mu naught upon 4 pi I dl bar cross r bar upon r cube. So we have to use now this result. Okay. Now see how to take elements. Let us now consider this is now straight wire which is carrying current. So current is now I. So I current is passing in that. So we want to calculate now at some distance, that is r. So we want to calculate here. So now what we are doing is, let us consider one small element on this wire. Take one small element on this wire, that is now at a distance y from here. I am taking from here distance y, an element of length dy. We are taking now from this line at a distance y, a small element of length dy. Now see, because of that small element, what is strength of the field at this point? Okay. Now see what we can do here. Let us join this element to this point. So we are now joining that current element to that point. So where we want to calculate now strength of the, suppose this makes an angle theta with this normal. This is normal to this line. Okay. This makes angle theta. Now coming to here, mu naught upon 4 pi I into dl bar. Direction of dl bar is direction of current. It is like this. Okay. R bar, position vector of the point where we want to calculate strength of the field with respect to this current carrying wire. That means direction will be direction of R bar. That will be, it will be like this. This is R bar. Okay. This is R bar. Right. Or do one thing to avoid confusion here. Let us take distance as d. Otherwise, having confusion here between this R and this R. So I am taking now this distance as d instead of R. But take this distance as d. Then it becomes now R bar position vector by d cube. Okay, distance becomes d. Now this is a d. This is now R bar position vector. Now we have to focus between dl bar and R bar. What is angle? See carefully. This is a theta. This is a 90. Then this will be 90 minus theta. Then this will be 90 plus theta. This is the angle between this dl bar and R bar. So I hope you are getting this one. Now use this one here. See what we get. dB equal to dB, that is equal to modulus value mu naught upon 4 pi I into, in the place of dl, I am taking out this length, we have taken dy, right? At a distance y from this line, element of length dy. So in the place of dl, I am taking dy, right? Next, if you take here dl bar cross R bar, that becomes dl into R into sine of the angle. One R gets cancelled, okay? So only dy. Remaining is now, it is angle between these two vectors. And that angle is now 90 plus theta. So it is now sine 90 plus theta. Okay. Right. Now see what else left. Here already we have taken R. So R cube. Remaining is R square. Okay. So I'm taking it is now distance of that point from this element. Remember, it is not D. Okay. I am repeating distance of this point from this element, because we are calculating strength of the field due to this element at this point. Therefore, distance will be d square plus y square under root. Okay. And we want r square. That's why it is d square plus y square. Okay. Like this, we have to take all elements from here to up to this end, and from here to up to this end, right? And you can see in this one, y is a variable, theta also variable. So it has now two variables. So we want to convert this into a single variable. Okay. You can see in the question, we are given angles alpha and beta. So we want to eliminate now D. Okay. See how to eliminate now D. From diagram, you can see tan theta equal to y by t, right? That means y equal to d tan theta, right? So we want to eliminate now y. So we have to eliminate now dy also, right? So to get dy, now differentiate this. So differentiate that, then see what we get. Dy equal to d into derivative of tan secant square theta d theta. Okay. Next, here in the place of y, d tan theta. So I can take d square outside. D square. Remaining is 1 plus tan square theta. It is secant square theta. See what we get here. db equal to mu naught upon 4 pi I in the place of dy. D secant square theta d theta sine of 90 plus theta. That is a cos theta. That is a cos theta upon it is d square d square secant square theta, right? Now see calculation part. So calculation part d, this is d square secant square secant square gets cancelled. Now see for remaining one. So db value mu naught upon 4 pi I into what else left? Cos theta d theta upon d. This is because of that small element. Like this, we have to take all elements. You can see here from 0 to alpha, that is a clockwise. From 0 to beta, anti-clockwise. So here we have to follow now sign convention. If I am taking alpha, means clockwise positive, then I can write here limits. The strength of the field, it is equal to integration of dB. Okay, integration of dB, that is mu naught I upon 4 pi d. It is a constant. Remaining is now cos theta d theta. Limits are minus beta to alpha, right? That means I have taken clockwise as a positive. We can see alpha clockwise, beta anti-clockwise, right? And this is completely our choice. Now see calculation part. Take this constant outside. Integration of cos theta d theta. It is sine theta. So mu naught I upon 4 pi d. Now take limits. It is a sine alpha minus sine minus beta. That is now expression for strength of the magnetic field due to a current carrying straight wire. Okay, it has a finite length. Let us see now if it has infinite length. See what happens. If this length extends up to infinity, then this angle becomes 90. See carefully. If this end is up to infinity, then alpha becomes 90. In the same way, if this end extends up to infinity, if you want to join, then that line makes angle 90. One is clockwise, other one anti-clockwise, and both are 90 only. That means the first thing is here, if length is infinite, okay, if you are taking infinite length, then see, so we are taking now current carrying wire, its length is up to infinity. So we want to calculate now at a point somewhere here, distance d. This extends up to infinity, here also up to infinity, right? Then alpha is 90, beta also 90. Means one is clockwise and one is anti-clockwise. Okay. Substitute that here. Sine 90 minus sine minus 90. Minus of minus becomes plus because sine minus 90 is minus 1. Minus 1 here minus. Okay. That means its value is now b equal to mu naught I by 2 pi d. Okay. For example, we are taking infinite length, but we want to calculate at one end. So we want to calculate now. So we want to calculate now at this end, infinitely long. Okay, distance is a d. This is up to infinity, right? Then see what happens. According to this diagram, in this case, alpha becomes 90, beta becomes 0. Okay, that means at this point, field becomes. So we are taking field at one end of an infinitely long current carrying wire. See what is this? We are finding field at one end of an infinitely long current carrying wire. That is equal to, see what we get? Sine 90, this is 1. And this beta value 0. So this is 0. So at one end, it is mu naught I by 4 pi d. Okay. So like this, we can take alpha and beta. So if you are taking finite bar, its expression is mu naught I by 4 pi d into sine alpha minus sine minus beta, right? Length is infinity. Then we are taking at this point alpha, beta, both are 90. One is clockwise, one is anti-clockwise. Expression is mu naught I by 2 pi d, right? Next, if you are taking at one end of an infinitely long wire, it is mu naught I by 4 pi d, right?